Hey everyone, my name is Adnan. I am another TA for CS170, and I will be going over some of your common questions this week. So James, what questions do you have for me?
Morning, Adnan. I wanted some clarification on master theorem. Uh, Oftentimes we write down this recurrence, which is like T of n, and then maybe there's some T of n's on the right side and some O of n's or theta of n's. Could you just clarify what each of these terms mean again?
Yeah, good question. So let's just go into a quick breakdown of what we're actually doing in master theorem for runtimes. So if you take a look at this blue tree right here, we have the sort of starting node of size n, right? And that is our like initial algorithm. Then what we're doing is we're actually breaking it into subproblems, right? We have what we call here the branching factor, and then b is sort of how much we cut down at each level. And that's what you can see here. We have, sorry, this should be a subnodes, not b. We have a subnodes of size n over b, and that's how much we're cutting down, and we're doing it a times. So when you have this question of what is t and what is o, right? What you can actually see, what you'll end up figuring out is that t represents not only this node here, but all of its subnodes and their subnodes as well, right? That is the entire runtime we are trying to calculate. It's the runtime of the entire tree. But what that actually entails is, well, we need to figure out the amount of work you do at this node, and then you also need to figure out the amount of work at the children. So what is the amount of work at the node? Well, that ends up being this O of n to the power of d term right here, right? We're doing O of n to the d work at that node. And then we're trying to figure out, okay, so now we know the work at this node. We need to figure out the subnodes, right? And we know that there are a of them, which is a branching factor. And we know that for each subnode, the input is n over b size. So what we're doing is we're actually just saying we're going to recursively find out what the runtime of that subnode is, and it's a times. So that's why we have this sort of Tn over b, which is that sort of recursive uh, amount. And that's why we also end up calling it a recurrence relation, because we're sort of implying the recursion through this sort of runtime equation.
I see. Could you clarify like what the difference is if we have a theta of n versus an O of n on the very end?
Right, yeah. So that's a good question. We generally use O of n, but both of them work. So like I said, in this case, O of n to the d is how much work you do at like this node and this level. So what is the definition of O and what is the definition of theta? Well, the definition of O is that we have a runtime that upper bounds the amount of work or like the runtime at that level. And what does theta mean? Well, theta is actually an upper and lower bound on that amount of work. So if you actually just back up for a second and take a look at uh, sort of what the sum of our work actually ends up being, it's, the work at this level, the work at this level, the work at this, or I guess you can't see that, the work at this level, the work at this level, the work at this level, and so on. And those are sort of encoded in this O or theta term here. And because of that, what we end up doing is actually just summing up all of these O terms and all of these theta terms. So that means that the overall runtime is also just O or also theta, because we're either just keeping that upper bound or we're keeping that upper and lower bound. So in summary, when you have this term as an O, your overall runtime will end up also just being O, because we only have the upper bound. But if it's theta, then you still have the upper and lower bound for your final runtime.
That makes sense. Thanks,
Awesome.
Adnan.
Yeah.
Actually, I had another question. This is not related to master theorem as much. It was with homework one, this is question 7. In some previous classes like 61C, we saw an algorithm for turning decimal numbers to binary by dividing them by 2 and then uh, using that remainder bit as like whether or not we should sort of record the ith digit as a 0 or 1.
Hmm.
Um, that seems pretty efficient to me. Can you explain why that doesn't work here or doesn't achieve the runtime that we want?
Well, yeah, so that's a great question. I think one thing that we tend to forget is when we're actually doing that division, it isn't actually a constant time operation. It is also linear. And specifically in this case, when we're doing, you know, a base 10 number divided by 2, because the 2 doesn't match up with the base, what we end up having to do is rewrite the entire number. So you end up writing n digits again, and that makes the operation linear time. And then, when you're saying we do it for every single digit, so n of these divisions, that makes it this sort of quadratic runtime of n squared. So that's why we end up not actually improving on the quadratic runtime that we're given in the problem. So let's just maybe go through what the actual solution does in the homework. So what we first do is we convert this input x into, the first half of the number and the second half of the number, which is a and b, where x is a times 10 to the n over 2, where n is the number of digits, right? So 10 times n to the 2, or n over 2. Sorry, back up. A times 10 to the n over 2 plus b, right? So that ends up making a and b n over 2 digits. So we're splitting it into this first and second half, right? And then we're recursively computing the binary representations of a and b. But what we're actually doing is we're also converting into a third subproblem, which is a, b, and 10 to the n over 2. We also need to calculate the binary representation of that. We can't just leave that out. So because of that, we have to convert the binary representation of that and then convert all of them back to x by doing a single multiplication, right? 10 to the n over 2 times a, and then adding b to that. So what our runtime ends up being is a master theorem runtime, which is, t to the n equals 3 t of n over 2 plus O of n to the log base 2 of 3, right? And the solutions go into a bit more detail, right? But we have 3 subproblems, so our branching factor is 3. We're converting it into halves, and those are n over 2 digits. And what ends up happening is when we're calculating when we're multiplying together, right? We proved in class that that's a runtime of n to the log base 2 of 3 if n is the number of digits, and that's the amount of work done here. So that actually ends up being, with the master theorem, n to the log base 2 of 3 times log base 2 of 3, or sorry, not log base 2 of 3, log n. And what you'll see is this actually improves on the quadratic runtime, like we intended to do for the problem.
I see. That makes sense. So is this assumption that like division, for example, takes linear time? Do we have to keep that in mind throughout the course?
Yeah, so that's a good question. I think you don't have to make that assumption anymore. From now on, what you're going to see is, let me just move this for you so it's easier to understand. Sorry. You should keep this note in mind in blue right here, that from now on, we will assume a model where the addition, the multiplication, and division are constant operations. It's just very special in this case because we want to help you understand how multiplication at a core isn't actually constant based on the number of digits of the numbers that we use.
I see. It's like a different computational model.
Exactly. Exactly. Yeah. Cool.
Cool. Thanks, Adnan. Yeah, one last question. I was working on question 9 in homework 1, and I was having some difficulty finding the overall runtime. I understood the algorithm, and I think I kind of have a recurrence relation, but I was wondering if you could explain a little bit in more detail how it actually derived the runtime.
Yeah, sure. So let's just quickly go through the algorithm, the main idea of the algorithm one more time. So what we're doing in the algorithm is we are just taking the matrix, we're going right into the middle pivot or the middle row, right? And we're trying to find the pivot of that. And then the idea is that we do this sort of a divide and conquer again, where we split it into, I guess you could say, the top left quadrant of the matrix. So everything to the left and above that pivot, and then everything below and to the right of that pivot. So you can treat it as like another sort of branching problem where you have the main matrix here, right? And then you're splitting it into the smaller matrix here, which you could think of it as this box here, and then the other matrix here, which you can think of as this box here, right? And when you think about it initially, you might think, oh, well, master theorem should work here, but that actually doesn't work, and I'll explain why. So if you look at this sort of graphical representation or visual representation, this is also from the homework solutions, you'll see that, okay, in the first level of recursion, you'll have the full matrix, but if you say the pivot is slightly to the left, like not exactly in the center, the subproblems actually are of different sizes, right? This one to the top left is at the first level of recursion is smaller, and the one to the bottom right is larger. And if you think about how the master theorem works, you have this sort of dividing factor B, and that is how you find like the size of the subproblems, and you assume that they're all the same size. But as you can see here, that's not the case depending on where the pivot is. And so because of that, that's one reason why you can't use the master theorem. And then another important reason is that when you're dividing into subproblems, you're not dividing by rows, right? You are trying to find the pivot you're not dividing by the columns, and that's what n is. You're dividing by the rows. You're trying to find the pivot for every single column. So as you keep going in deeper, 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 you'll find that the actual height of this entire of this entire tree is actually log base m. And what that means is in the master theorem, you won't just have this, it won't be dependent on just n, the number of columns. It will also be dependent on m, the number of rows. And because of that, you'll have two variables in the master theorem, or two variables in the recurrence relation, and the master theorem won't be applicable. Cool. So let's just go through how you might actually calculate based on this tree your final runtime, right? So what are we actually doing? What we're doing is we are trying to we're branching off into these two halves, right? And we know that although the number of rows or the number of columns is uneven between the problems, the number of rows is. We're splitting into half of the columns above and half of the columns below. And what we're doing is we're trying to like scan through the entire width of the matrix, or half of the width of the matrix, to find that pivot. And let's just take a worst case scenario. Let's just say the pivot ends up being the furthest to the left it can be, or the furthest to the right it can be, right? In this worst case scenario, you might have to span a factor of time that is linear to the actual input, width of the matrix. So like it's a linear amount of work. And okay, well, so now we know that the subproblem may at worst to be linear time. Well, what you can see is that if you look at all the subproblems, if you look at the second level of recursion, the subproblems never overlap, right? They're always the one subproblem is to the left of the pivot, one of them is to the right of the pivot, and when you actually look at combining all of the widths together, you'll see that at each subproblem level, you never exceed the width of the original matrix, right? N. So what you can say is that because you're scanning over the entire width and it's linear to that, the amount of work that you do at each level never exceeds n, right? It's O of n. So what you can see here is the work at each level is O of n, O of n, O of n, right? And So now we know that the work at each level is O of n, and then we just established earlier that because we're splitting the number of rows into half, the actual depth of the tree is log of m. So now we've just figured out both halves of the runtime. So we can just multiply these together, and then we get that our runtime is equal to O of n log m. And that's it. And you can see that you don't end up needing the master theorem, right? And even then, the master theorem is sort of derived from this idea of recursing through this tree to a certain depth and you're doing a certain amount of work. It's just that because the master theorem doesn't apply, you have to do it a bit manually.
I see. So you're like saying like we compute the work per level in a different way, but it's like a similar idea.
Exactly, exactly.
Gotcha. All right. Yeah. Thanks, Adnan. That's all the questions I had.
Awesome. And thank you everyone for listening to this. Hopefully you learned a lot more about, master theorem and these homework problems and the idea of divide and conquer.